My name is Matthew Portman, and this is my presentation on identifying optical counterparts from follow-up of gravitational wave events. So as an introduction, time domain astronomy is the study of transient astronomical events, or transients, that vary over short cosmic timescales. Our research focuses on identifying electromagnetic transients, or counterparts, to gravitational wave events and observations from the Dark Energy Spectroscopic Instrument, or DESI, and the subsequent follow-up. These counterparts may only be visible for days to weeks, so timing in the development of an optimal observation strategy is crucial. Our research additionally focuses on specific phenomena, such as kilonovae, resulting from binary neutron star or neutron star black hole mergers, which are difficult to observe due to their dimness and short lifespan. As a whole, transients are of high interest to the astronomical community. We hope that by identifying counterparts to gravitational wave events, we can work towards resolving the discrepancies between different measurements of cosmological parameters and better understand the role of transient phenomena in the evolution of the universe. To perform this follow-up, we have developed a pipeline picture that ingests the data received from gravitational wave observatories and identifies transient candidates in the event's localization map. The pipeline works by first reading in the map and identifying the 90% confidence interval, or contour, of that map. It then queries transient alert brokers and identifies both these alerts and previous observations from the Dark Energy Camera Survey, or DCAM, in the contour to create a target list for the telescope to observe. The pipeline also provides the means to classify and analyze the resulting observations, but work is still ongoing to automate this process. I want to emphasize here that finding a match to a single gravitational wave event is essentially a guessing game, heavily informed by our previous observations and strategy. Without automation, this task would be nearly impossible, hence the need for the development of this pipeline. As for gravitational wave follow-up, the image to the right is an example of a localization map from a gravitational wave event in 2019, which is overlaid with output from our code that includes follow-up pointings performed by DESI at the time of the event. The blue dots inside the green area, which is the localization contour, the confidence interval, I should say. Blue dots are matches to transient alerts or previous observations in that area, again by DCAM, and that's what's output by our code. So these matches indicate any potential candidate for follow-up observation. Our pipeline will ultimately be able to dictate where to point the telescope and what to point the individual targeting fibers at to maximize coverage of priority targets. The GIF to the left shows a visualization of an optimal coverage strategy for the event at the right. This strategy was determined by a code called main injector, developed for DCAM, that has been repurposed for DESI and implemented into the pipeline. We do hope to identify kilonovae in future data for both observational interest and to constrain the theoretical rate of kilonovae events. So by observing or conversely not observing kilonovae, we should be able to estimate a limit on the rate of kilonovae in neutron star black hole or binary neutron star mergers. A second goal to these determinations is to provide a metric for and to evaluate our machine learning classification scheme. So since these events are so rare in terms of the sensitivity of our current gravitational wave instruments or observatories, we intend to evaluate the algorithm's performance in regards to false positives and further refine it in the hopes of finding a real kilonovae event. So here's where the matching with previous observations comes in. The image to the right details our analysis of the previous DCAM observations. In running these observations through our classifier, we did not find any potential kilonovae events according to our prescriptive threshold of 99% probability, according to the classifier. Although this does not provide any insight towards the classification of false positives, it is in line with the expected rarity of kilonovae events, again in terms of the sensitivity of our current gravitational wave observatories. So to conclude, we're on track to have the pipeline ready for the anticipated return of LIGO in December of this year. This includes the development of the follow-up routine and any means of analysis to identify those potentially interesting transients. Thank you.